Welcome you all. Okay, in the last session I explained to you about the concepts of smoothing in frequency domain. So we can perform enhancement filtering operations both in spatial domain and in the frequency domain. So in the frequency domain we modify the Fourier transform. So in the last class I explained smoothing filter. So smoothing filter is mainly used for attenuating high frequency values. So sometimes edges and noise pixels are contribute more in the image. So in order to eliminate or in order to attenuate the sharp changes, means noise or edges, we use a smoothing filter. So in smoothing filter mainly three types of filters. One is ideal low pass filter, Butterworth low pass filter and Gaussian low pass filter. So low pass filter or smoothing filter is attenuating all high frequency values. So it attenuates certain high frequency values and it passes only the low frequency values. So here high frequency values may be sharp edges or noise will be attenuate, and it allows only the specific range of intensity. So when we performing smoothing operation, we need to specify the cutoff frequency. Based on the cutoff frequency, it attenuates all the high frequency values. So above the cutoff frequency, frequencies are eliminated or attenuated, and the remaining frequency will be allowed. So the output of smoothing filter is the blurred output. Output of this smoothing filter is the blurred output. So in the ideal low pass filter, the frequency values within the cutoff range that will be allowed, and above the frequency values will be eliminated. So the equation for the ideal low pass filter is h of u comma v is equal to 1 if d of u comma v less than d0, less than d0. Otherwise 0 will be assigned. So within the cutoff frequency, within the distance value, the frequency will be allowed, and above the distance value will be eliminated. So in the ideal low pass filter, d0 is cutoff frequency and d is distance value. So the d will be calculated by using euclidean. Next, in the main problem of ideal low pass filter is blurring effect and ringing effect. So if the distance value is less, the cutoff frequency is less, then ringing effect is more and blurring is also more. So if distance is increased, means d0 is increased, then the blurring effect will be less. So similarly, the next Butterworth low pass filter, in the Butterworth low pass filter, ringing effect is less compared to ideal low pass filter, and the last filter is Gaussian low pass filter. So in the Gaussian low pass filter, the filtering operation is done based on the order. So in Gaussian low pass filter, blurring effect and ringing effect is less. So there is no ringing effect if the distance value is high. If the distance value is high, then there is no ringing effect. So in this class, in this session, I am going to explain one more filtering, that is sharpening filter in frequency domain. So in frequency domain, there are two types of frequency, low frequency and high frequency. So high frequency are rapid changing, fast changing frequency, and low frequency is a slowly varying frequency. So highly varying frequency or high frequency is considered as edges and the noise pixel. So in the sharpening filter, so highlight the frequency values, certain frequency values, and attenuate the frequency which are less than the cutoff frequency. So this is reverse of low pass filter or smoothing filter. So smoothing filter, we attenuate the high frequency values, but in sharpening we attenuate the low frequency values. The value is less than the cutoff range, cutoff frequency, that is d0. So sharpening in frequency domain is represented by ideal low high pass filter, that is HHP. H indicates high pass high pass filter of u comma v is equal to 1 minus HLF. HLF stand for low pass filter of u comma v. So, this is the inverse of the low pass filter, that is a smoothing filter. So, here 1 minus low pass filter output. So, once again here also 3 filtering methods. One is ideal, high pass filter, ideal high pass filter. So, this is IH, PF ideal low pass filter. Second one, Butterworth high pass filter. Butterworth high pass filter, BHPF, and the last one is Gaussian high pass filter, GHPF. Okay, there are 3 filters: ideal high pass filter, Butterworth high pass filter, and Gaussian high pass filter. So, here the operations is the reverse of the ideal low pass filter, Butterworth low pass filter, then Gaussian low pass filter. Okay, let's discuss the first method, that is ideal high pass filter. So, in the ideal high pass filter, the equation is h of u comma v is equal to 0 if d of u comma v less than or equal to d0, otherwise 1. So, in ideal high pass filter, h of u comma v is equal to 0 if the distance value is less than d naught. So, in ideal low pass filter, if the d of u comma v is less than d0, that becomes 1. But in the case of ideal high pass filter, if the value distance value is less than d0, then it is become 0, otherwise 1. So, the graph is d0, this is 1 and 0. The graph is 0. This is h u comma v and distance value d of u comma v. So, if the d of u comma v value is less than 0, then this part becomes 0, and if the value is above d naught, then this value is 1. So, this value is 1 and the below d0 value is 0. So, here we can represent this as, okay, here in the ideal high pass filter, this is u comma v, this is h of u comma v, So, it allows only high frequency values above the cutoff frequency and below cutoff frequency will be attenuated. So, below cutoff frequency will be attenuated. So, the output is so the center value this value is 0. This is 0 means black, and the surrounding value is 1. The surrounding value is 1. So, this is white fixer. So, in the ideal low pass filter, the center value is 1, and the surrounding value is 0. So, the center is white and the surrounding is black. Okay. This is about ideal high pass filter. So, here if the distance value D0 value is 0, D0 value of 6 or 5, 3, then blurring effect is more. If you increase the distance value or cutoff frequency value D0 above 50 or 30, then blurring effect is less. Blurring effect is less. Okay. Let's see how this ideal high pass filter works. Okay. Okay, this is a perspective plot of the ideal high pass filter, Butterworth high pass filter, and Gaussian high pass filter. So, in the ideal high pass filter, it allows only the frequency above the cutoff frequency. So, if it is below the cutoff frequency, that will be attenuated. So, in ideal low pass filter, the center value means the radial value is white, but in the ideal high pass filter it is become black. So, here it considers the radial distance between the center pixel to the surrounding pixel. So, within the distance it is less than the cutoff frequency becomes 0, and above cutoff frequency is 1. So, you can see in this plot. So, the value is less than D0 becomes 0 and greater than D0 is 1. Okay, here there is a fixed cutoff 0 and 1, but in Butterworth high pass filter and Gaussian high pass filter, the center pixel start with black and slowly change to white. So, here in the Butterworth high pass filter, it depends upon the order of n. So, order of n. Okay, you can see here this is the ideal smoothing filter, ideal low pass filter, Butterworth low pass filter, and Gaussian low pass filter. So, in the Butterworth ideal low pass filter, the value less than cutoff frequency is white and the remaining pixel is black, means 1. So, here less than cutoff frequency is 1, above cutoff frequency becomes 0. So, here you can see here the order n to order 1, 2, 3, 4. Here it allows only the frequency less than cutoff frequency, and it attenuates all the frequency above the cutoff frequency D0. Okay. Similarly, is a Gaussian low pass filter. So, the main difference between the ideal low pass filter, Butterworth low pass filter, and Gaussian low pass filter is the ringing effect. Okay. Now, you can see a sharpening frequency domain filter. So, in the ideal high pass filter, there will be a ringing effect. In the Butterworth high pass filter, little bit ringing effect compared to ideal low pass filter. Then there is no ringing effect in Gaussian high pass filter. There is no ringing effect in Gaussian high pass filter. So, just now I explained the ideal high pass filter. So, in the ideal high pass filter, the cutoff frequency is less than D0 becomes 0, greater than D0 is 1. So, D is a distance value and D0 is the cutoff frequency. So, you can see in the output, if D0 is 15 and D0 is 30, there will be a ringing effect. So, you can see in the first image, so the circles are not clear, the edges are not clear, there will be a blurring effect. Okay. In the second image, D0 is 30, little bit ringing effect and blurring effect is less. So, if your D0 is 80, then there is a clear image, the fonts are clear, then circles are also clear, the edges also clear. Okay. Where in the ideal high pass filter, there will be a ringing effect and blurring effect. So, there is a more ringing effect in the ideal low pass filter with cutoff frequency low. Okay. This is a code for performing ideal high pass filtering and frequency domain. Okay. First we read image.
So here I am reading an image of type TIFF. So first I will get the size of the image, that is n, then FFT2. So I already mentioned in the previous session, in MATLAB, in order to perform discrete Fourier transformation, we use an inbuilt function FFT2. So here we get a Fourier transformed output. So according to the equation, this will be f of u comma v. Next, here D0 cutoff frequency. So here I have set cutoff frequency as 60. Next, we need to find the distance value. So for finding distance, here I'll use u and v. So we get a u and v value. So u and v value is, that is 0 to m divided by 2 and 0 to n divided by 2. So after that we get the grid, means the matrix of the filter function, that is EH. So here D is equal to square root of u to the power plus v power, means here we find u minus m divided by 2 whole square plus v minus n divided by 2 whole square. Okay, that is the equilibrium distance formula. So here we have calculated equidistance. Next, the function h, that is a filter function h, can be obtained by checking d greater than d naught. So in the low pass filter, we check d less than or equal to d naught, but in the case of high pass filter, we get greater than d0. So h is equal to double d greater than d naught. So once this value is satisfied, the value of h becomes 1. Next, we multiply h with the filtered Fourier transform image, that is ft image. So g is equal to f into f of u comma v, that is ft image. Later we get the real part of the image. So the output image is equal to real inverse Fourier transformation of the g output, g of u comma v. So it is inverse Fourier transformation of g. Okay, here we are getting only the real part. Later we display the output input image and the output image. So you can see that. Okay, you can see here the input image and the output image. So here d is 60. If I set d value, you can see there is a sharp edges is extracted from the image. Okay, this about ideal high pass filter. Okay.
Okay, then next is the Butterworth high pass filter. So in the Butterworth high pass filter, the filtering is performed based on the distance value and the nth order. So here we specify the order n. So the equation is d h of u comma v is equal to 1 divided by 1 plus d naught divided by d u comma v to the power of 2n. So in the Butterworth low pass filter, the formula is h of u comma v is equal to 1 divided by 1 plus d of u comma v divided by d naught. So in Butterworth low pass filter, if the frequency value is below the cutoff frequency, then the value is slowly vary from 0 to 1. Okay, in the Butterworth high pass filter, the center pixel value is this the center pixel value is 1 and it slowly changed to black. But in the Butterworth high pass filter, the center value start 0, then it slowly changing to 1, So here the output depends upon the nth order. So if the nth order is 1 or 1 or 2, then distance value is cutoff frequency is 5 or 10, then there is more ringing effect and blurring effect. There is more blurring effect and ringing effect. So you can clearly observe this is slowly change from 0 to 1, means the center pixel value start with black black and outer is white. Outer is white. So here the value is slowly varying from 0 to 1, 0 to 1. Okay, this is about the Butterworth high pass filter. Butterworth high pass filter.
Okay, this is the equation for Butterworth high pass filter. H of u comma v is equal to 1 divided by 1 plus d0 divided by d of u comma v to the power of 2n. So in ideal low pass filter, h of u comma v is equal to 1 divided by 1 plus d of u comma v divided by d naught whole square. But in the case of high pass filter, d naught divided by d of u comma v. So compared to ideal high pass filter output, so in ideal high pass filter output there is a ringing effect, but you can see here there is no ringing effect and there is a smooth transition in the output. So you can see here here little bit ringing effect in the distance d0. If we increase the distance value d030 and d080, then there is a smooth transition. There is a smooth transition. The edges are clear. There is no blurriness in the edges. Okay. This is the code for Butterworth high pass filter. Butterworth high pass filter. So here I'll consider same image, cameraman image. Then first we read the image. Later we perform discrete Fourier transformation, that is FFT2. Then nth order 2. Then the distance value means cutoff frequency is 50. After that here we are finding the distance value. Okay, that is d. D is equal to square root of u minus m divided by 2 whole square and v minus n divided by 2 whole square. Next we calculate the function, filter function or filter mask value, that is 1 divided by 1 plus d naught divided by d to the power of 2n, d to the power of 2n. So here we calculate the filter mask, that is h. Later we multiply h with the Fourier transform image, Fourier transform image, that is f of u comma v. Okay, now I'll run this program. Okay, this is the output, input image and the output image. Okay, this is about Butterworth high pass filter.
Okay, the next filter is the Gaussian high pass filter. So Gaussian high pass filter is represented by h of u comma v is equal to 1 minus e to the power of minus d square u comma v divided by 2d square. So here the filtering is occurs on the distance value, that is cutoff frequency value d. So cutoff value is d naught. So we can also consider d naught as a sigma value. So d naught is equal to sigma. So here we consider d naught is sigma value. So sigma is a cutoff frequency. So here the center pixel value, center frequency value is black and it slowly changes to white pixel. So here you can see here, if the cutoff frequency is d naught, cutoff frequency is d naught. So here the intensity value start from 0 and slowly varying to slowly change to 1, slowly change to 1. So here the if the distance value is 0, distance value cutoff frequency value is low, then more blurring effect. If cutoff frequency is high, then there is no blurring effect. There is no blurring effect in the output. So compared to ideal low pass filter and Butterworth low pass filter, in the Gaussian filter there is no ringing effect. There is no ringing effect in the Gaussian filter, but there is a ringing effect and blurring effect in ideal high pass filter. Okay, this is about the Gaussian high pass filter. Gaussian high pass filter.
Okay, the next is the here is a formula for high pass Gaussian high pass filter. H of u comma v is equal to 1 minus e to the power of minus d square u comma v divided by 2d. naught square. So in the Gaussian high pass filter, there will be a smooth transition. There is no ringing effect in the output. There is no ringing effect in the output. But in the case of ideal high pass filter, there will be a ringing effect. But in Gaussian high pass filter, there is no ringing effect. There is no ringing effect in Gaussian high pass filter. Okay, this is the example output of Gaussian high pass filter. Okay, this is output of Gaussian high pass filter. Okay, this is a MATLAB code for Gaussian high pass filter. So here I consider same cameraman image. So first I'll read the image, then I'll get the size of the image n. Then this line perform discrete Fourier transformation of the input image A. Then we perform transformation. Okay. After transformation, we do the shift operation. Then here m by 2 n by 2 means center of the image. So P and Q are the center of the image. So I'll calculate center of the image. Then from P and Q, I calculate the distance value. Repeatedly. So I'll consider the first pixel and first row, first column pixel. Then I'll find the distance. So distance is SQRT I minus P to the power of 2 and J minus Q to the power of 2. So the formula, this equidistance formula is square root of U minus M divided by 2 whole square plus V minus N divided by 2 whole square. So here P is M by 2 and Q is N by 2. So I'll calculate the distance value. Then here is a formula for Gaussian 1 minus exponential of distance. So distance represents d of u comma v. D of u comma v to the power of 2 divided by 2 into d naught square. So d naught square is the cutoff frequency. So in this case, I am giving the distance cutoff value as 10. So for cutoff value 10, I am calculating later. Inverse transformation. So in this line I am doing inverse transformation. So image original is equal to IFT shift inverse of shift operation, that is a filter apply. Later I'll get the image form, that is absolute of IIF shift. So this is inverse of shift function. This is inverse of discrete Fourier transformation. So inverse of discrete Fourier transformation. So here I'll get the inverse transformation of the filtered output. Later I'll display the output image. Okay, this is the MATLAB code for performing Gaussian high pass filter. So you can see the output. So this is my input image and this is the output of the Gaussian filter. So here you get the sharp changes. So it highlights the sharp changes. If in case, if you specify the distance value, cutoff value 2, you can see the output. So here, compared to previous output, this output is clearer than the previous one. Okay, clearer than the previous one. So if in case if you give more cutoff value, you can see here, it highlights only the high intensity values. It highlight only high intensity values. Okay. This is about Gaussian high pass filter. Okay, there is one more program to demonstrate Gaussian high pass filter. So in this program, instead of using shift, I just use a discrete Fourier transformation. So first I'll read an image. The image is of a color image. Then the image is converted into grayscale. So this is a function for converting RGB to gray. Then the function FFT2, you already know this function is used for performing a Fourier transformation. Next, here x and y coordinate. So this is used for finding the distance function. So this is the function, the statement for performing a Gaussian low pass filter. Similarly, here after finding the Gaussian function, here we do the transformation. Then here I am performing filtering operation. After that, I am displaying the output with the visualization of the filter function. Okay, now you can see the output. Okay, this is the input image. This is the input image, and there is the Gaussian function, Gaussian of the input, Gaussian filter of the image. Then this is the high pass filter output. Then this is the low pass filter output. So you can see the difference between the high pass filter and the low pass filter. So here the high intensity values are highlighted and low intensity values are suppressed. In the case of low pass filter, so high intensity pixels are attenuated and it allows only low frequency value. Okay, there is a visualization of Gaussian low pass filter, Gaussian low pass filter. So you can see here it allows only the frequency and it attenuates all the high frequency values. Okay, similarly, this is a visualization of Gaussian high pass filter. So here it allows only the intensity value above the cutoff frequency and it attenuates all the low intensity value, low frequency values. So in this example, so I have specified the distance value is 5. So in case if you increase this value to 15, and now you can see the visualization of Gaussian high pass filter, Gaussian low pass filter. Then this is the high pass filter output. So in the previous case, the value is 5. So there more pixels are highlighted, but in the case of 15 cutoff frequency, you can see there are more intensity values allowed in the low pass filter. So it reduces the blurriness. So if in case increase the distance value, that is a cutoff value to high, then the output of the low pass filter is looks good because the blurring is less. So there's one the filter function. Then is the input image. Now you can see here, if in case if I increase this value to 50, then you get more clear image in the low pass filter output. Okay, there is a visualization of the Gaussian high pass filter, then visualization of Gaussian low pass filter. Then there is the output of Gaussian high pass filter. So here only small part of the butterfly is highlighted because it contains the highest intensity value. Then there is the output of low pass filter because here I have specified the range, cutoff range is 50. So here cutoff range is 50, so you get more clear output. So less blurriness. Okay, less blurriness in the output image. Okay, this is about the Gaussian high pass filter